Hey everybody, and welcome back to Geology 311, Stratigraphy and Basin Analysis. This is the lecture content for week 10, which begins our third and final unit of the semester, where we're going to be exploring basin analysis, the role of tectonics, and also looking at some basic trends in stratigraphy throughout North America over the last 700 million years or so. So let's get started with this week's lecture on basin analysis, tectonics, and sedimentation. The three main aspects for today, or this week I should say, really are looking at the roles of subsidence and isostasy. We're going to look at how we classify our sedimentary basins and a couple of analytical techniques for them as well. The overall theme here is how do we make space for our stratigraphic record on a crust. If you think about it, we have sedimentary units that are thicker than any depositional environment on the planet. So how do we actually make the space for this massive amount of sediment that's accumulated over hundreds of millions of years? First thing first, though, what exactly is a basin? We should probably define what one is before we get into analyzing them. A sedimentary basin is anywhere on the Earth's surface that is dominated by subsidence. That's it. This is a place where we are accumulating sediments because this particular part of the crust is subsiding more than uplifting. So these can accumulate over 10 kilometers of sediment in a basin, because the more you add into your basin, the more it flexes the crust, the more you promote subsidence. For example, the deepest basin on the planet is about over 15 kilometers deep, and this is the Caspian Sea in the Gulf of Mexico. These are incredibly deep basins, and they just keep accumulating sediment because there is this active subsidence going where the more sediment you put in, the more the flex of the crust occurs. Well, now that we've identified a basin, what about basin analysis? This is any detailed and integrated study looking at sedimentary rocks, but really in a basinal context. It's important to note that we have to look at the entire sedimentary basin as a whole, kind of as an enclosed system, so to speak, but looking at what's going on above and below, especially in the asthenosphere. So obviously, we do basin analysis because it's important for understanding geological history and also other economic considerations. So there's a lot of applications here. Boiling things down with sedimentary basin analysis to the very basics, you are defining and describing a sedimentary basin based on the sediment first. You want to analyze the sediment. What is the composition, primary structures, internal architecture of the rock itself. Now, describing the basin components is also important too. So this is why even in courses like this, we start with some basics in identifying sedimentary rocks, but then we go into the basinal components, such as looking at what's going on in the back arc portion of the basin, the fore arc portion, the passive margin, the epicontinental portion, and our extensional basins. So each one of these components is a place where we can be accumulating sediment because we have subsidence taking over. Now let's start looking at some of these, starting with the back arc region. This is defined as the area behind a volcanic arc. So we're looking at the back arc region here. And these can come in a variety of different styles. In island volcanic arcs, such as what we might see in Japan, the back arc region of the back arc basin is going to be the basin of oceanic crust that has some considerable abyssal depth to it. Okay. This could be separated by older remnant arcs that are similar to little island volcanic arcs, but maybe are extinct. The continental arc of the back arc region is going to be part continental platform, which could either be dry land and subaerial exposure or forming a shallow marine basin. So any time that you have subduction going on and you have a volcanic arc, the back arc basin is going to be what's being deposited on the non-subduction side of your volcanic arc itself. Okay, so we're not talking about moving the magmatic arc at all. It's what's going on the non-subduction side. Now our forearc area is going to be here on the subduction side. This is that depressed area between the subduction zone and that actual volcanic arc. So it's everything that's going to be pretty much deposited here in yellow. So it's important to note that the architecture is going to be very different between our back arc basin and our forearc basin, meaning the way that our sediments are actually stacked. Because in the forearc, it's going to be filled with sediments from that adjacent landmass. It's going to be from the magmatic arc itself, but also it's going to be including material that's trapped from the ocean crust as it's being subducted. So the entire accretionary prism and forearc basin are part of this region. To shift gears a little bit, our passive margin regions and associated passive margin basins are very, very different than what we see with our active margins, whether it's the forearc or back arc. In this case, we're looking at the transitional material that's going on between oceanic and continental crust. So there's no active plate margin here. But this is where continental crust grades into oceanic crust, and the sediment on top is essentially covering an ancient rift. So as we have these downfaulted crustal blocks from when rifting initially happened during continental divergence, we're now seeing that covered in an apron of sediment that is going to also be continually subsiding because it's sitting on top of old, dense oceanic and continental crust. Our epicontinental regions and the basins associated therein are a little bit different than the previous ones we've looked at. In this case, you start out with uplifted terrain. In this case, we're looking at the old Ordovician tectonic orogeny, which is mostly eroded away. But as sediment sheds off of the tectonic, it's going to pile up in what is now the Central Appalachian Basin. On the other side of that, you have the relatively minor uplift Cincinnati Arch. So you have this low, stable crustal block that's just being pressed down because there's tectonic highs on either side of it. So these are really different kinds of basins. The central portion of the Appalachian Basin is characterized by lots of evaporites and carbonates because of limited circulation. So you're going to see tidal flats and sands and shales kind of around the edge, and then in the inside there's just not a lot of places for that water to go, so you start getting a lot of evaporites and carbonates. So we'll talk more about epicontinental basins as we kind of continue through this last unit. Our extensional regions produce very specific kinds of basins, pretty much what we see in the Basin and Range out west. So with like the Sierra Nevadas and the Wasatch, you have very brittle deformation, overlying ductile deformation during extension. So you have a lot of downfaulting blocks, rotational and translated blocks, with small basins forming in between. So we'll take a look at more of these too in the upcoming weeks. So as we start to look now at the role of subsidence and isostasy, there's a couple of questions we want to think about as we move forward. What kind of thicknesses do we see in our sedimentary basins? And how can we accumulate anything on the continental surface in places where we normally don't accumulate lots of sediment? What processes are going to be the ones promoting the development of a stratigraphic record? And where is this accumulation most likely to happen? So these are some of the things we want to keep in mind as we're looking at these roles between subsidence and isostasy. So here's an example of the kind of problem that we're dealing with. Here is Monument Valley in Four Corners out west in the US. These red sandstones that you see represent shallow water and continental facies. And we are talking about deposits that are literally hundreds to thousands of feet thick. So how can we get these types of thick sequences that represent shallow water environments to accumulate on the continental surface? So this isn't on ocean crust, this is on the continent. Well, let's look at broader than just Four Corners. Here's Grand Staircase, so the composition of Bryce Zion and Grand Canyons. Here we're looking at about 10,000 feet or about 3,000 meters of thickness. So it's more than just four corners. Okay, so we have 10,000 feet of thickness. This is, again, on a continental shelf. This is on the continental mass itself. This isn't on oceanic crust. Well, what about the deepest lakes today on Earth? Our deepest continental depositional environments today would be Lake Baikal in Siberia, which is just about 5,387 feet. That's incredibly deep. But we're not accumulating the types of sediments we get in Monument Valley here. So how do we actually do this? So how can we get these incredibly thick sequences of continental and shallow water facies that accumulate in a continental surface? It all comes down to crustal balancing of mass, where we have vertical density profile changes, but the integrated mass remains roughly the same. Let's look at an example. Keep in mind that the crust itself essentially floats on top of the mantle. So if we have a series of blocks floating in a more viscous medium, we have three different sizes. We have a very tall middle block, very, very thin or shallow blocks on the ends, and kind of an in-between sandwich in between our two extremes. Notice that our thickest block not only stands the tallest, but also has the deepest root down into our modeled mantle. The same goes for our other two sizes. You're kind of looking at a pretty even split between what's above and what's below. But we have a bit of a paradox here, because unlike our previous example where we showed the blocks on the water or viscous material, our mass is not just staying in one place. Sediment is constantly being redistributed. With tectonic uplift, you now cause erosion, which moves sediments around. You have subsidence, which is putting sediments somewhere else. So we're constantly moving our crustal masses around in the forms of sediments. When we do this, how can we get any kind of gravitational balance to exist? Well, we have to look at the sum of layer thicknesses and densities of columns that are essentially equal. So we're going from a very tall column of sediment to a number of more shallow columns that are spread out over a larger distance. This is where the role of isostasy comes in. And where we take loose material, in this case continental crust, at the top, you add the mantle at the base to make up that mass. So if you shave a bit off the top, the mantle pushes up an equal amount. We can also think of this as the waterbed effect. If you load the crust, there's subsidence. So I don't know if you've ever been on a waterbed, or a trampoline is another example. You have mass. If you sit on the waterbed or the trampoline, you are causing subsidence. But on the other side, you are promoting uplift. This is what makes stratigraphic space. The more sediment we accumulate, the thicker the sequence that we are storing. However, the more we have erosion, the more it promotes the mantle to push upward on that flexed crust. So there's another example I like to give. If you were to be doing something really, really stupid and dangerous, like stand on a trampoline and you have somebody get on your shoulders, again, very stupid thing to do. When you stand on that trampoline, you're going to be promoting subsidence. When they get on your shoulders, you are promoting double the subsidence, or a considerable amount more. Now, in this case, our mantle is the springs of the trampoline. If you remove that upper person, you aren't going to completely balance it out. You are going to just uplift enough to make that space to make up for the amount of subsidence that has been removed. So there is a bit of a mass balance here, or close to a mass balance. So plate tectonics and isostasy both play a considerable role in how we produce a basin. To make a tectonic basin, you have to have some kind of a subsiding foreland basin. You have to have crustal flexing and crustal loading, all working in tandem. Together, you're going to get a fully subsiding, continually subsiding tectonic basin. And this is all really happening from convergence, though. That's why we're talking about the foreland basin. So let's look at a short animation that kind of walks us through how this works. So here we have our lithosphere overriding our asthenosphere. We have a very thick continental lithosphere that has a deep root, and we start to uplift it. As we do so, we see the initial subsidence, and now the more we uplift, the more we shed sediments into that basin. We have continued deposition along with uplift off to the side. Notice that as the mantle continues to push up on that lower portion, we're getting close to balance, but now we've pretty much uplifted as much as we're going to. Now erosion takes over. And so we now see uplift cease, and we keep piling sediments into our basin, continuing to flex the crust downward and produce incredibly thick sequences. So the main three controls of any basin is going to be first the sediment supply. In other words, are you uplifting enough sediment from a source area to continuously have a supply? In our previous animation, once we would start uplifting, we were shedding sediment off at the same rate, so we had a pretty good supply of sediment until we weren't uplifting anymore, and then when erosion is the only thing taking over, we don't have that uplift anymore, ultimately you are going to run out of sediment supply at some point when you hit mass balance. But subsidence plays a major role here too, because we have thrusting and flexing of the lithosphere, which is really controlled by your regional tectonic activity. But the more you load the crust, the more you flex it. Also, sea level and climate play a huge role here too, which is something we didn't talk too much about, but we're going to get into that. The amount of, how that controls erosion is going to be very important. Now, we've got these three controls: sediment supply, subsidence, and climate or sea level. But I want to make something very, very clear, and that's that the magnitude of these controls is important, but not nearly as important as the rates of sediment supply. The rate of subsidence and the rate of change in climate play much bigger roles than any one of them in their own solitary magnitude. And there's actually a number of different mechanisms that can promote crustal subsidence. So you can have crustal thinning, where as you are extending or stretching out your lithosphere, you have erosion during uplift, or any kind of magmatic withdrawal, which is going to thin the crust, is going to promote subsidence. Any kind of mantle or lithospheric thickening, you have a cooling of the lithosphere, and then stretching or heating of the asthenosphere itself is then going to promote that thinning and that flexing downward with subsidence. Obviously, any sedimentary or volcanic loading, as we've already talked about. Tectonic loading, local isostatic compensation. So when you have the crust and regional lithosphere flexing, this could really be depending on just what's going on in the underlying lithosphere. Well, we have subcrustal loading. This is when the lithosphere flexes during any kind of underthrust, where you have a very, very dense lithosphere. It's important to remember that not all lithosphere is the same density, right? Changes in asthenospheric flow or any kind of crustal densifications can also promote these types of flexing, of subsidence, or as we press the crust downward into the mantle. And when we look at these subsidence mechanisms, we can also graph these out into our different types of basins, whether it's a divergent basin, an intraplate basin, and our convergent, transform, and hybrids. These are all different types of basins we're going to be discussing in upcoming lectures. And as you can see, the more bold our line is, that's where we're seeing really, really dominant subsidence mechanisms. So for example, in your divergent basins, especially in terrestrial rift valleys, crustal thinning plays a huge role in subsidence. However, in your convergent trenches, tectonic loading plays a much more dominant role in subsidence. So, and as you can see, when we start looking at the subcrustal loading, asthenospheric flow, those are all pretty minor overall. You can see just looking at the bold bars which ones are the most dominant. Tectonic loading and crustal thinning are two of the most dominant types. However, sediment and volcanic loading play very, very important roles in all of these as well. So kind of a short lecture this week, but I just wanted to go over these kind of basics. And just to summarize, looking at how we deliver sediment to a region can activate what we need for mechanisms to actually make that stratigraphic space, to make that basin. So isostasy plays a huge role, the way that we flex the crust. So these mechanisms are all provided by tectonics. As we move the crust around, we redistribute sediments. And we have the flexing of the crust upward and downward in the form of isostasy and subsidence. So to answer our question of how do we produce all of this accommodation space, well, the sediment supply itself makes the accommodation space because we have a planet that has a lithosphere that flexes because we have a asthenosphere underneath it that provides mobility for that flexure. So we'll continue this next week with a slightly different perspective on it, which is looking at tectonics and accumulation, how we can accumulate these very large packages, especially depending on the type of facies. So we will see you next time.